The problem is that we would train our classifier just on 50% of data, and we will never use the other 50% for the data for training. And this sucks, because very often we don't have so much data. So what is the solution to this? What do you think?
Cross-training.
Oh, wow.
I'm working with implementation.
Do you know what is cross-training?
I'm guessing I train and test both of them, something like that.
So this is cross-validation, cross-training. So what happens here is that you split your data set in 5 or in 10 folds, and then you take one to test on, and you take the remaining 4 to train. And then you rotate 5 times, and then each of the folds is used for testing exactly once. And then on these test folds, you assemble the performance of your entire classifier. So you get the performance on this set, on this set, on this set, on this and this. You take them together, you divide by 5, and this is the performance of the classifier. Clear? Yeah. Okay. One way to establish the performance is just to count how many instances from all instances are predicted correctly. Yeah? Okay, this is called overall accuracy. This is what we often use. The problem with it is that imagine you have in your data set 90 samples of class A and 10 samples of class B. If you always predict A, then you're correct in 90% of data of time points, which is not so good, right? If you always predict just one class, the overall accuracy would be 90%, but this is not true. Yeah, so a better way to establish the performance is to use area under the row curve. Are you familiar with this one?
The area under the curve, yeah.
Yeah?
Yeah.
Okay, so then I will do it very, very briefly. Okay, so your classifier, when it makes a prediction, it always gives some kind of confidence value. For Bayesian classifier, this is the probability, and for SVM, this is the distance to the hyperplane. So these are our confidence values. All right. Some of our predictions that would be correct predictions, and some of them that would be would be true positive predictions, and the others would be true negative predictions, because we are working with two classes. A perfect classifier does the separation like this. A classifier that is worth nothing does classification like this, and most of the time it does the classification like this, right? So our job, your job, is to find the threshold, this threshold, that you will move to the right or to the left, so that either to minimize the number of false positives, but then on the other hand the number of false negatives will increase, or you move it to the left where you increase the number of false positives, but then you decrease the number of false negatives. So you have to find the threshold that separates leads to a better performance. Anyways, by moving this threshold, you can plot sensitivity versus 1 minus specificity, and you will get such a curve. It's called a row curve. And the area under the row curve, this is the whole area. And the perfect classifier returns something like this, and this kind of classifier returns something like this. We should see in our Pokemon data something like this.
And what is the specificity and sensitivity?
Here.
Oh, fine. The true positive divided.
Yeah.
So the TP, I'm guessing, is the surface, right? The area of the...
TP?
Yeah.
This is the number of true positives.
Oh, just the number, okay.
Yeah.
Right.
So at 100% confidence, we have maybe 2 predictions that are true. Okay. At 90% confidence, we have maybe 5 that are true, and this is how it's done.
I understand.
Yeah. And then by moving threshold, you can plot such a curve. So this is something that we will be going after when we do our classification. All right. So in the wiki, we told you that there are JavaScript machine learning classifiers, and this is true. However, I myself, I have to admit, I'm not a JavaScript person so much. So I myself, I have never tried those. Feel free to try, but before we do that, I really want you to do this machine learning with Beka, because this is a platform that is I am most familiar with, so I can help you a lot. And this is a good platform to know about anyways, because really everyone in academia is using it. So you can download it, maybe also now or later. Maybe later. I will still be around so that you can play with the data. Okay, so what is Weka? Weka, that's a bird in New Zealand, looks like this. And this workbench also comes from New Zealand. It was developed by these two guys. He was actually visiting us at some point, and it was very, very cool talking to him. So it was great. So this workbench is developed for data mining tasks. There are really many classification algorithms. I introduced 2 today, but actually there are over 100. So you will be quite busy trying them. You don't have to try them all, but some would be nice. There are algorithms for data pre-processing and analysis, which you will also apply, some of which, clustering and so on. And there are also algorithms for feature selection. Weka is Java based and it supports really all platforms, so it's really cool to try. So now I want to give you a presentation, a demo presentation of how it can be used. So this is the GUI. You go to Explorer, and then a window like this opens. Okay, it asks you to open a file. As you can see, I have prepared some files. Now we open it. Let me show you how this file looks like. So the ARF, this is the input format for your data. These are comments. Okay, this is the name of the file. This is the name of your task, whatever you're doing. These are attributes. They're defined like this. And if you remember, I was talking about these 20 attributes, the alphabet of amino acids. So here I define them. I say that there are these 20 attributes, and they have a numeric value because we were counting them, 1, 2, 3, and so on. Okay, so these are 20 attributes, and then the last attribute always is the class. In your case, it will be prediction. Will appear, will not appear. Yeah. Okay, and here comes the actual data. So you see here we have our vector. It has 20 attributes, and this is the class. And this is the whole structure of our data.
This was manually inputted or was like retrieved from somewhere automatically, this matrix?
You can do both.
Okay.
Yeah. In your case, you will write a program, I guess, that will convert. No, you will get the data from the database of project A.
Yeah.
Exactly. So it will be done automatically. But this is the structure. Okay, so you import it in your Weka, and then the first thing you see the composition of your attributes. You see that your your first attribute is presented this often, 20 times, 21 times altogether. Yes, the minimum value of A is 0, the maximum value of A is 13. And then you see it for everything. And here you can also check out the composition of your classes. In my case, it's 50-50. Okay, you can visualize your attributes. You just need to increase the point size to make it more visible, and jitter to spread them across the window, and then it looks like this. Okay, so I agree that it's not that visible when you work with so many attributes, but if it's separable, maybe sometimes.
So with this data, you are not able to predict anything.
Hold on.
No, I mean, you said it's like.
This is a toy example on biological data. Yeah.
So do you predict something with this? Like
I'm not predicting anything yet.
Okay.
I'm just checking out my data. I'm just looking at what's the composition, whether my features, if they make sense.
Okay.
Yeah. So what I'm
When you work, you focus on a segment of block or something?
yeah. So look, this are my 20 attributes,
Okay.
20 features, here and here, and then they are plotted one against each other. And then I want to see, do these features, do they actually make sense to have in my data? Do they provide any separation of my data? Okay, and here it's like, well, it's going to be a tough job.
Basically, by visualizing here, you see which ones make sense to
Exactly.
use them in the
Yeah, this is just to give you some kind of sense of
like
your
for
data.
example, time, would it make sense to include time, and then you see that they're all matched up together and you cannot separate them? It's like, yeah, I'll just remove time, use another feature.
For example,
Okay.
yeah.
Okay.
So this is like, it's just good to see with the eye.
Yeah.
Okay. So this, for example, this L, it seems to be a good one,
Yeah.
right?
Good?
Yeah. Because
Yeah.
you can see a lot of reds
Yeah.
at the bottom.
And blues on the top.
Blue are separate, so
Yeah,
It-
but still, like, because there are some of them red.
But it will be
together.
most often the case, yeah.
Okay.
There are also automated ways of doing feature selection. Let me see. So this is the automated way of doing that, and it will tell us. I will write on Weka all these parameters.
Okay.
And what we see here is that this L seems to be indeed the best attribute for doing classification. The next one is F. So see, we recognize it by the eye.
Because like the first one, it looked like it was better. If you go to the visualize and you go to the in top, is it like the first
This?
one? Yeah.
This is, no. This is,
Oh, it's a class.
yes.
Yeah, it's a class. Okay.
Exactly. So this is exactly the same as this one, but here you do your human analysis, and here you do the statistics. This is just math behind it.
Yeah.
but this is always reliable.
Yeah.
Because it's mathematics.
Yeah.
You cannot.
Yeah. This is nice to see, to look at. This is like real stuff. So you see, so you see that there are some features that they even have a negative contribution. They're just confusing your method. So these ones you probably don't want to include. So these ones you would then have to cut out. And how you do this? For example, H. We go to our data, we click on H, and we say remove. It's gone.
Okay.
Yeah. We can do again. So L is still on top, and so on. So maybe it makes sense. Look at the contribution values. We have here something like 8%. That's like a lot. Wow. This one we really want to have 2%, and so on. And then at some point, they're going to be like 0.6 or so. So maybe it makes sense to even make a cut somewhere here.
Yeah.
So this is one of the ways for you to optimize on your training data. So this is for you to try out actually, where to cut the features. So what you do, you start with as many features as possible. You plug in whatever you think makes sense or not. For example, when we were doing this machine learning on Game of Thrones data, we were even thinking on putting stuff like how many words does a character say. Nonsense like this, but it might even help.
Yeah.
So first you put really everything, and then you start cutting, because this thing is going to tell you what's important, what's not. Yeah. So say we found our features, and then we do classification. This is the classify tab, and these are our over 100 machine learning methods. We find base here, and there are already like 10 different bases implemented. We go for a simple one, and we do classification. So just click on start, boom, it's done. This is the classification. Okay, this is our confusion matrix, where we can see that altogether of 50 instances of class +1, 40A I predicted correctly, 8 I predicted wrong. Yeah? And here it's the same, it's 10 wrong and 40 correctly. This outcome is summarized in statistics, shown here: precision recall, accuracy recall, F measure, which is combination of the previous two, and our rock area. Yeah?
What is
The rock area. If you remember my slide with the curve, rock curve. This is the area under the rock curve. So a perfect classifier would have a rock area of 1. This one is like
Close.
very close to 1. So,
What's the full form of ROC? What does it stand for, ROC?
receiver operating curve.
Okay. But in the slide it was not there when you...
It was.
ROC?
Yes, it was. Here.
Yeah, it's like.
So it gives you this value, area under the curve.
Okay. Yeah.
So almost 90%, almost 100% accuracy. Is this good or bad?
It's good.
So if we get 100% prediction, is this good or